We will now apply the divergence theorem to 3 examples where we are calculating flux. And these 3 examples are all going to be fluxes through closed surfaces that we calculated in a previous video on surface integrals. So here we want to apply the divergence theorem. So we're going to recognize that the surface integral, which represents flux over a closed surface, is the integral of f dot ds. And that can be rewritten as a triple integral over the enclosed volume of the divergence of f dv. Our first example is to find the flux of the vector field f equals x, y, 0 through the tetrahedron formed by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Now, when we did this example previously, we had to calculate the flux through each of the 4 faces of this tetrahedron. So that required us to do 4 surface integrals. Now we're going to apply the divergence theorem in order to make this calculation with 1 integral. So the first thing that I need to do is to calculate the divergence. So the divergence of f is going to be the derivative of x with respect to x, or 1, plus the derivative of y with respect to y, which is 1, and then the derivative of 0 with respect to z, which is 0. So the divergence is actually just a constant, 2. So now if I apply the divergence theorem, I'm going to do a triple integral over this volume of the divergence of f dv. So that's going to be a triple integral. And we're going to integrate from z equals 0 to z equals 1 minus x minus y initially. So we're going to integrate up in that direction. And we're going to integrate the function 2 dz. Now, if we want to describe the region in the xy plane, you can see that that's a triangular region where y is equal to 1 minus x. So I'm going to integrate from 0 to 1 minus x dy. And then I'm going to integrate from 0 to 1 dx. So now we need to find this integral. So I'm going to pull out a 2. And I'm going to have the integral from 0 to 1. And then the integral from 0 to 1 minus x. And then the integral of dz is just going to be 1 minus x minus y dy dx. So that's 2 times the integral from 0 to 1. And now I'm going to integrate 1 minus x minus y dy. So I'm going to get 1 minus x times y minus 1/2 y squared. And then all of that is going to be evaluated between 0 and 1 minus x. And then I have to integrate that dx. So this is going to be 2 times the integral from 0 to 1 of 1 minus x times 1 minus x, also known as 1 minus x squared, minus 1/2 y squared, or 1 minus x squared. Substituting in y equals 0 will give me 0. So I'm going to integrate that dx. Now this simplifies nicely because 1 minus x squared minus 1/2 times 1 minus x squared is just 1/2 times 1 minus x squared. So I'm going to get 2 times the integral from 0 to 1 of 1/2 times 1 minus x squared dx. Those 2's are going to cancel. And so when I do this final integral, I'm going to get a minus 1/3 times 1 minus x cubed evaluated between 0 and 1. Substituting in 1 will give me 0. And then I'm going to add 1/3 times 1 when I substitute in 0. Okay, and so the flux is actually equal to 1/3. So that actually ended up being a much simpler integral to do than the 4 surface integrals that we did in a previous video. Now I would like to find the flux of the vector field f equals xyz out of the region T. It's bounded by a paraboloid z equals 1 minus x squared minus y squared and the plane z equals 0. Okay, again, I'm going to compute the divergence of f. Okay, derivatives with respect to x and then y and then z are going to be 1 plus 1 plus 1 or 3. So again, we have constant divergence. And now I want to do the triple integral of the divergence of f to calculate flux. And when I do that, then that becomes an integral or double integral over the circle x squared plus y squared equals 1. And then the integral dz will be from 0 to 1 minus x squared minus y squared. And I'm going to integrate 3 dz dy dx. But hopefully what you see here is in the xy plane, I have this nice circular region. So this is better described in polar coordinates. So in fact, I'm going to rewrite this as 3 times the integral from 0 to 2 pi, the integral from 0 to 1, and then the integral from 0 to 1 minus r squared, and that's going to be r dz dr d theta. So I can think about this as being 3 times the integral from 0 to 2 pi d theta, and then the integral from 0 to 1 of r times 1 minus r squared when I integrate dz, and then this will be dr. So let's take it another step. Okay, so this will be 3 times the integral d theta is going to be 2 pi. Okay, I'm going to rewrite this part as r minus r cubed. So that when I integrate, I'm going to get 1/2 r squared minus 1/4 r to the 4th evaluated between 0 and 1. So this ends up being 3 times 2 pi times 1/2 minus 1/4, so that's 1/4. And so this will end up being 3 pi over 2, which is what we got when we did 2 surface integrals in order to calculate the flux through the paraboloid, which is the upper part, the upper surface, and then the unit circle, which formed the lower part of the surface. Okay, let's do one more. This one is going to be the flux of the field F equals z k hat through the surface S, that's the upper half of the spherical surface, rho equals 2. So I've drawn the spherical surface here where rho is 2. I'm going to calculate the divergence. The divergence in this case is just going to be 1, which is really nice. And then I'm going to do the triple integral of the divergence of f dv. Okay, but essentially I'm integrating over that volume 1 dv. And so this is just the volume of the hemisphere. So what is the volume of the hemisphere? Well, it's going to be 2/3 pi times 2 cubed. And in fact, that's going to be 16 pi over 3. And again, it was much simpler to do this, this divergence integral than to do the surface integral that gives the flux through the surface of that hemisphere. So hopefully this demonstrates the power of the divergence theorem. When you're working with flux through a closed surface, it is much easier to do a triple integral over the volume than to do a surface integral, or possibly several surface integrals.